All right. In this video, I'm going to tell you a little bit about the origin of prompt and how it grew into Skynet. And then I'm going to show you the basics, absolute basics of how these optical telescopes work and how we can turn uh, the images that we collect into a color picture. So first, just a few fun images. This is a picture of Cerro Inter-American Observatory. It's our best site on the Skynet system. It's in the Chilean Andes. The prompt telescopes are these tiny ones right here. The bigger ones on the top of the mountain, they tend to be more manually controlled. Although these are small, they're fully automated. That's their advantage. Okay, sorry that this is so small, but it's a fun little video. When we built the site, uh, so I got to UNC Chapel Hill in 2002, got the money to start building the site in 2004. By December of 2004, we started construction and built it over the next 6 months or so. And we set up a webcam that took a picture every 10 minutes. And when we were done, we pieced it all together. It was like a 45-minute movie. So we cut out the nighttime and the bad weather, etc., and got it down to about 60 seconds. And you can notice the sun moving across the sky on a periodic basis here. The money was raised in two chunks. So four of the domes are farther along. Then you can see the other two domes. We just lost the tarp on one of those domes during Chilean winter. And then we had purchased two more domes and finished the site with the second grant. Now the site's expanded. We now have more telescopes there, larger telescopes, but these are the original six. Here's a little movie of what happens every night. The sun gets 1 degree below the horizon and the domes open automatically. The little telescope in the front is just an amateur telescope. It's not part of Skynet. You see the person walking in the back, he's working at that telescope off on the right, which back then was manually controlled. Anyway, the dome's open and you see all the telescopes slewing into position to take the initial calibration observations. These are flats. We actually image the bright sky to illuminate all the defects in the cameras and use these flats to correct our later astronomical images. You may notice this telescope's different looking. That telescope is slightly different and it hadn't been deployed yet when we made this movie, but it's there now, along with two whole new structures. Another thing you may notice, these are clamshell domes. They open completely. The telescope is completely exposed to the elements. And this is because these telescopes were originally designed to find exploding stars called gamma ray bursts. In fact, they were designed to find the most distant explosion then known, which we did in September of 2005. So it did not take us long for the telescopes to achieve their mission. That led to all sorts of funding. I could hire lots of people who actually know what they're doing with hardware. Me and my grad student, we kind of faked our way through this initial build. And I built a great team of hardware engineers, software engineers, and expanded into a global network. Here's another picture at Tololo. And this is actually what it looks like at night. It's just amazing. You look up, you see the Milky Way. You give your eyes a little bit of time to adapt, but you'll see stars like you never have. That bright star there, it's not a star, it's planet Venus. Here's another image. This is the Prompt 7 telescope. It's one of our later builds. It's a 32-inch telescope. All the originals were 16 inches, so twice the diameter, 4 times the collecting area. But I include this here so you can see these two little splotches here and here. Those are the Magellanic Clouds, little baby galaxies that orbit our Milky Way galaxy. You can only see them from the southern hemisphere. And here's another fun picture from the webcam. This is a storm coming in. Often when we're there working, we're working above the clouds, but sometimes they come up and envelop us. Still, it's a great sight, 300-ish good nights per year. Most of the bad nights occur during our summer, their winter. Here's me standing next to one of the baseline systems. to make it look cool. No, for scale. And so this is a 16-inch diameter primary mirror. Over time, through different partnerships, we've upgraded some of these. Here we have a 24-inch, which also fits in these small clamshell domes. As we do these upgrades, we push the smaller ones out to other locations around the world. So we now have a number of prompt sites. Chile, we have 3, 4, 5, 6, 7, actually 7 telescopes there. We opened a site at the National Observatory in Australia, Siding Spring Observatory over here. And it ran for a couple years before it got electrocuted. There was electrical surge. I've since raised the money to repair the equipment, and hopefully this will be back online this semester. On the other side of Australia, we've opened 2 sites separated by about 100 kilometers. One's in Perth and one's at a dark site east of Perth. So we have great coverage in the Southern Hemisphere, can watch things almost continuously as the Earth spins. For Northern Hemisphere coverage, we had 2 sites in Canada. This one's near Athabasca, an auroral monitoring site. I was part of the build for that, and you see the aurora. What you can't see in the picture is when the northern lights turned on, the coyotes started howling. And they were close, and they were 360 degrees around you, something you just don't notice until they speak up. Now, we've since moved this telescope over to University of Saskatchewan. They have 2 of our telescopes. One of them will be going to Mount Lemmon in the U.S. Southwest. These are the prompt telescopes. These are the ones that UNC has paid, raised the money for, maintains. They're great sites, great hardware, uniformly good quality. Then we have our partner telescopes. Lots of people have come to us with systems that can be controlled remotely and ask if they can go on our Skynet scheduling and analysis software. The answer is almost always yes. We know how to control pretty much any type of commercial equipment out there. And this map's a little out of date. We do have a scope in Poland, another one in Perth, and a bunch across the US and Canada, but they come and go. Some are really high quality and some are not. Some are in bright city locations. It's a mixed bag, but you have access to these as well. And we'll make use of some of them in the MW course. Okay, now I'll talk about the radio telescopes in a later video. Now that I've introduced you to Prompt and Skynet, let me just walk you through the basics of how a telescope like this works. So here's our baseline system, 16-inch diameter primary mirror. And the most important part of the telescope is not the telescope. It's actually the least important part of the telescope. All the other parts, attachments, are more important. Most important part's the mount. Now in this picture, that's an old style mount. They don't make those anymore. There are better ones out there. But your telescope observes a very tiny part of the sky. Take your fingers and make that little box-like shape and hold it at arm's length and hold it up. And that, look through it. And that's kind of the field of view of these telescopes, very small. And so the telescope's riding on a mount. The mount needs to be able to point very, very accurately. And it needs to be able to track. Remember, the telescope sitting on Earth. Earth is rotating. So these mounts are rotating at the same rate as Earth, but in the opposite direction to counter out the rotation. So you stay on your target. If it doesn't do that well, you end up with a streaked image. So the mount is very, very important. Now, if you look at the yellow line, that's the path of the light. It comes down, bounces off the primary mirror, comes up, bounces off a secondary mirror. With a telescope like this is where we do the focus. We can move that secondary mirror in and out. Very small amount. You can't even see it with the eye, but that allows you to focus on the camera down below. The light bounces off the secondary, goes through a hole in the primary mirror. That makes this a Cassegrain telescope. You see this tube here, a light baffle. It keeps stray light out. Now, normally with a telescope, the whole thing is encased in a tube. Most telescopes you've seen are probably encased in a tube. But we can't do this here, not with these clamshells. These telescopes are exposed. And if I put the whole thing in a tube, the wind will push on the tube, shaking the telescope, ruining the images. So these are completely open optical tube assemblies. The wind mostly goes through, allows us to observe in higher winds. Anyway, The light goes through the light baffle, through the hole in the primary, and into a filter wheel and a camera. Here's an example of a wheel. This is a 5-slot wheel. It has a red filter, a green filter, and a blue filter, and some kind of clear open filters. Some of our filter wheels have 17 slots. We had some specially made so we can hold not just red, green, and blue, but all sorts of different filters that pros and amateurs like to use. So we're sending the light through one of these. So suppose you rotate the red filter into the optical path, then only red light will pass into your digital camera. Here's an example digital camera. A lot of our telescopes still have 1K by 1K cameras. That's 1 megapixel. That's far less than what's on your phone. Some of them have 2K by 2K. That's 4 megapixels. Still far less than what's on your phone. But one of our 1K by 1K cameras may cost $15,000, and a 2K by 2K may be $60,000, $70,000. It's because these things are designed to see in the dark. Your cell phone camera is not. If you don't believe me, go lock yourself in a closet and take a selfie and see if anything comes out. That's my homework assignment to you. No, don't do that. I'm just kidding. But these are very sensitive. Basically, the light comes in. This is like under a microscope. You can see what's there. It goes in, and you see it's a bunch of cells. As the light comes in, it strikes an electron. The electron ends up in the cell or the bucket, and it accumulates for as long as you integrate, as long as you expose. And then it reads out. In the CCDs, the older style cameras, and in CMOSs too, what happens is the charge reads out row by row. Up here, you see technology to read this row. It reads it out, and then each row passes its charge to the next row, reads out, passes, reads out. Eventually, you read the whole thing out. Okay. And then you have a number. You have an array in your computer. How many electrons knocked into their buckets by photons, light, accumulated in each bucket, in each cell. And then you can colorize it. If it's a lot, here it's colored white. If it's not a lot, it's colored black. Sometimes we invert this. We make the stars black and the background white. It's arbitrary. This is what we call a grayscale image or a monochromatic image. Now, on your cell phone, you use, it's a color detector. It has red, green, and blue sensors. That's not good enough for an astronomer. Astronomer want to know how much red light's under the blue sensor and how much blue light's under the green sensor and so forth. So we just use these monochromatic sensors and we change the filter. And so we put a red filter in, we make a black and white or monochromatic or grayscale image of red light. Put the green filter in, we take a grayscale image of green light. Same with the blue and with any other filter we want. We're not limited to red, green, and blue in the setup. Okay, then you read it out. So here's a picture of a parrot, a very red parrot. And so you can see the image that comes out when using the red filter is very bright because there's a lot of red. The parts of the parrot that are green, like the leaves back here, not the parrot, but in the picture, the leaves are green, so they're bright in the green frame. And there's a little bit of blue in the tips of the wings that comes out bright in the blue frame. You then colorize each and you add them together. It sounds simple. Sometimes it is simple. Sometimes it can get very technical with lots of detail, and we'll ramp you up as we go. Okay, that's the basics of prompt, Skynet, and how, kind of the baseline system works and you make a color picture.